So last class we started looking at these controlled these two-port parameters in little bit more detail, and we figured out how to use these two-port parameters. Okay, once you know the two-port parameters of any network, you can actually replace that network by a set of 4 elements, okay, which can be used to analyze the rest of the network if needed. That was the basic idea. Suppose you are exciting this network with something, okay, and so you have some network which is connected to this particular two-port. You want to replace the two-port by some simpler equivalent, and that, as it turns out, consists of 4 elements. Depending on what kind of two-port parameters you have, you can replace it by a certain set of elements. In the case of the Y parameters, you had at the input port, okay, the Y11 of the two ports will be replaced by a parallel resistance or conductance. The value of the conductance is Y11. But along with that, you know that the current is the sum of Y11 V1 plus Y12 V2. So you need to have a second parallel element. The second parallel element is nothing but a voltage controlled current source, okay, of value Y12 V2. Okay, the value of the current should be Y12 V2. The controlling variable is V2. Similarly, on the second port, you have Y22 in parallel with Y21 V1. If you take the Z parameters, the voltages are additive, and therefore you get a set of series elements. You get a series resistance of value Z11, okay, and in series with that you have a current controlled voltage source of value Z12 I2. On the output port, you have Z22 in series with a current controlled voltage source of value Z21 I1. And similarly, you can do the same thing for the H parameters and the G parameters also. Okay, so you will get a mix of parallel and series combinations. But the basic idea is any two port for which you know any one of these parameters can be replaced effectively by one of these equivalents. What would be the use of these equivalents? Well, with 4 elements, the assumption is that you might be able to analyze it very easily. A simple example could be something like this, right? Suppose I just have a network for which I know the two-port parameters. I apply a voltage, and I have a load resistance. I want to find out what happens, right? How much current is drawn from the supply from this voltage V1? How much current is flowing in R and so on? I don't need to analyze this network every time I want it for a different value. I just replace that network by its two-port equivalent, which is just 4 elements, and it will be very straightforward to solve it. Okay, that is the basic idea. You figure out the two-port parameters using a very simple procedure. We have seen how you do that, right? You either short circuit or open circuit depending on what kind of parameters you want, okay, and you get the two-port parameters in 2 steps. After that, you connect something outside this, you can figure out what happens. That is the basic idea. Now, we finished up with that, and then we moved on to something slightly different. Okay, so we said let's take a network composed of resistors, and let us say it is driven by a voltage V1, and what you have done is you have actually pulled out one of these resistors R inside the network outside, okay, across the 2 ports 2 prime, and let's call this 1 prime 2 prime. Now let us say this resistance is not R but R plus delta R. I want to find out what happens, for example, to this current IR, which is now IR prime. I want to find out what happens to this I1, which is now become I1 prime, and so on, right? I want to find out an easy way to figure this out. What could be the practical significance of something like this? Well, in reality, if you actually build a network with resistors, for example, what you'll find is if you go to the market and try to buy a resistor, right? If you go to the electronics shop and try to buy a resistor, it always has something called tolerance, right? You try to buy a 100 ohm resistor, it's not exactly 100 ohms. They'll tell you it's 100 ohms plus or minus 10%, plus or minus 1%, maybe plus or minus 0.1%. You can get different tolerances, but there will always be some variation, right? and you want to find out, how much, what happens to these other parameters, the sensitivity of these other parameters to this change in resistance, right? Because your circuit itself may be sensitive to these resistive parameters. Okay, so let us say this resistance is now actually R plus delta R. I want to find out what is, IR prime, I want to find out what is I1 prime, and so on. And when we were looking at this last class, I said you have to use reciprocity and substitution theorem. How many of you tried to solve this? Okay, a few of you. How many of you tried to solve the other reciprocity theorems? We did the case when you have a current at the current source at the first port and a current source at the second port. Did any of you try the other cases? Okay, so I'll quickly state the result for the case in which we have voltage sources, because I'm going to use that in the proof today. So the basic idea is, I have port 1 prime, and port 2 which is 2 prime. Okay, I'll take a resistive end port. So if you had to state reciprocity in very general terms, what are you trying to do? In very general terms, what you are trying to say is, you are applying some excitation at port 1, you are observing the response at port 2, okay, and you are taking the converse case when you actually apply the excitation at port 2 and finding the response at port 1, okay, and you are trying to find out the relationship between these two. Okay, that is what reciprocity is all about. Okay, we did the simplest case, or one of the sub cases where the excitations were using current sources, okay, and the responses were voltages. In reality, you can figure out what reciprocity means for the other cases also. In our case, we said that in the case of Z parameters and Y parameters, the reciprocity turns out to be Z12 equal to Z21. Similarly, if you figure out the other cases of reciprocity, you will figure out relationships between G12 and G21, H12 and H21. Okay, you can figure it out. I don't want to spend too much time on this in class. Okay, this is something, once we have done it for one case, it is very straightforward. What is going to be relevant here for us? Okay, I am going to figure out what will happen when the excitations are voltages. I will give you the result and use that to prove this. What happens when you get R plus delta R? Okay. So we'll consider two cases. So let me redraw it a little bit better. So N is a network composed purely of resistors. Okay. In this case, I am going to apply a voltage source VA, and I am going to define certain currents and voltages. Okay. In this particular case, I am applying a voltage and looking at the short circuit current in the second port. This is analogous to the case where I actually applied a current at the input port and looked at the open circuit voltage. Okay, I am doing this, I am giving you the result for this specific case because this is what we plan to use for our proof. In the second case, I am going to apply a VB here. Okay, so now I am looking at the short circuit current here. These are all hat quantities. Okay, and if you actually apply reciprocity, how do you apply reciprocity, or how do you prove reciprocity? You apply Telegan's theorem. follow exactly the same procedure we did in class for these two cases. So apply okay, you apply Telegrand's theorem, and what you will get is I2 by VA equals I1 hat by VB. Okay, this is the result you will get for this case. And what do you think it means for us in terms of the Y parameters of the two port? You are applying a voltage and looking at the short circuit current. What kind of Y parameters would be relevant here? Sorry, what kind of two port parameters would be relevant here? The Y parameters. Okay, so what this is telling us is that Y12 is the same as Y21. Okay, that is what this is telling us. If you actually do the case for the G parameters and so on, G parameters and H parameters, you will get other relationships between the 2-1 and 1-2 parameters. But we are specifically interested in this particular result. So let us go back to the problem that we were trying to solve. I have a very specific case where I had a Vs voltage source. It was drawing a current I. Okay, I had a resistor R. It had a current IR and a voltage VR, let us say. Okay, and I am looking at the case where I want to find out what happens when this resistance becomes R plus delta R, right? What happens when the resistance changes by a small amount? Okay, now these currents will no longer be IR, they will be IR prime. I will replace that as IR plus delta IR. So the small change in resistance causes a small change in the currents flowing in the circuit. Through the resistance, the change in current is delta IR. Okay, and so the current flowing out of the voltage source Vs is I1 prime. I'll denote that by I1 plus delta I1. Okay. Now what I'm going to do, let's take this R plus delta R resistance. Is that clear so far? Okay. This R plus delta R. Okay, I'm going to redraw it like this. Okay, and I'm going to use substitution theorem. Okay, to replace that. So what is this current flowing through this R plus delta R? IR plus delta IR. Okay, and this delta IR, I am going to replace it by a voltage source using substitution theorem. Okay, what is that equivalent to? IR plus delta IR times delta R, right? The voltage, I need to replace it by a voltage source which is the voltage equal to the voltage across this delta R resistance. Any questions? I am going to use substitution theorem only on delta R. Why am I going to do that? Because the original network still had R. Okay, I want to create a parallel between the original network and this network. So this I am going to say is approximately equal to IR times delta R. I am going to neglect the delta IR times delta R term. Okay, because that is going to be much smaller. Is that clear? So now Okay. This is my new network. Maybe I should start. This is A, this is B, and this is C. This is my new network, and this is I1 plus delta I1. I1 plus delta I1 is flowing here. Any questions so far? Okay. So far I have used two properties. One of them is substitution theorem. Okay, I am replacing delta R by a voltage source equivalent to the voltage across it. Number two, I am using the one of the original conditions which we started off with, which is that delta R is very small. Okay. I'll also write that down here. Delta R is extremely small. So I'm looking for very small changes in resistance. Now what do I do next? Now this is a network consisting of resistors. Okay. I can apply reciprocity. I can find out what will happen when I just apply Vs alone and not IR using superposition. Then I would short Vs, apply only IR times delta R, find out what happens. I will be able to calculate what is the change in I1. Okay, my final, I guess the objective is to find out delta I1. Okay, because originally this was proposed to figure out what happens to the change in power delivered. Okay, if a resistance changes by a small amount, what is the change in power delivered to the network? Okay, that is how this started off. But of course, once you know the two-port parameters or once you know the network, you can actually do it, find out the change in any, you can find out the change in IR, for example, and that has been denoted wrongly. You can find out delta IR, okay, or without using the two-port parameters, if you just picked out another resistance, you could figure out what happens to the current in that and so on. Okay. How will you use reciprocity? You apply superposition, find out the first case. The first case is when this voltage source is shorted. Okay. This voltage source is shorted. What is that case? That is the same as case A. Okay. That is the same as this case. You already know the solution for that particular case. Okay. So case B, okay, is going to be the case when we short Vs and apply IR times delta R alone. So I am shorting Vs, so this just becomes a short circuit. So IR times delta R, and this current of course is only delta I1. Okay, it's no longer I1. It was I1 plus delta I1. When I apply Vs only, there is an I1 current that flows. When I remove Vs, the rest of it must be delta I1, right? What is the current that flows here? Delta IR. In the original case I had IR. The current that flows here must be delta IR. Right? Okay. Now I am going to apply reciprocity between the cases. Between A and D. I said the first case is A, the next case is D. Okay? What will you get? Can you please use this result and tell me what you will get? I have given you the basic result for reciprocity when you have two voltage sources. Can you please tell me what you will get? use this result on A and D. What is I2 by VA? What is I2? I2 is the case for case A, right? It's the current in port 2. What is that? IR, right? And the exciting voltage is Vs, correct? So IR by Vs should be equal to minus, why is it minus? Because the direction of delta I1 is opposite, okay? So delta I1 by times delta R. Is that okay? IR by Vs is minus delta I1 by IR times delta R. All I did was I just used this result. What does it say? I2 by VA. Okay, I2 by VA is I1 hat by VB. Okay, that's all. That's okay. So what? That is okay. You can just use the, you can club the resistance here and look at the voltage outside that resistance. The resistance can be clubbed inside the network. There is no problem. Right? There is no problem with that. Okay, I'll give you a simple example between these two. Okay, I'll give you the connection between these two cases. Suppose I had the original reciprocity theorem was in the case where you are taking port 2, okay, and looking at the short circuit current. Suppose I had defined port 2 for these two networks for case A, okay. If I had said port 2 this was 2 and 2 prime, and I had included the resistance inside the network, and I'll do the same thing for case C also, okay. I can pull this resistance inside the network. I'll have the same graph inside the network. It won't change. Okay. That is why you have to figure out how to apply reciprocity, substitution and so on. Okay. While keeping the network the same. But or rather, to put it differently, you will need to figure out how to apply these cases even when you have these kinds of elements outside. Okay. They can actually be clubbed. As long as the two networks are the same, you can still apply Telegan's theorem. Is that clear? Entire which? What do you mean entire thing? The resistor and the voltage source cannot be replaced by a voltage source. No, it cannot. No, we don't want to do that. Right? We are trying to find out the relation. If you decide to do that, right, then the two networks are not the same. You can't apply Telegan's theorem. The reason we are doing it is this way is to apply Telegan's theorem and figure out reciprocity while having the same network. That can be done only when you separate out delta R voltage source. Okay. Go back and think about, okay, have you done this case applying reciprocity with voltage sources? You have, right? Okay. So it is defined as the short circuit current. You have a network, you apply a voltage source, you have a short circuit current. Correct? If you have a resistor here, what you would obviously do is pull in the resistance into the 2 port and look at the short circuit current, correct? Isn't that right? That is what you would do. You would define this network as including that resistor also. And that is what we are doing here. Any questions? Any other questions? Okay, so what did we want to find out? We wanted to find out delta I1. Delta I1 is minus IR squared by Vs times delta R. Okay, so this tells you what would happen if you have a delta R, what will be the delta I1. Now does this sign of, does this negative sign make sense? If you increase the resistance, the current should decrease, right? And that is what you expect. Okay, that should be expected, so the negative sign also makes sense. Okay. Now this particular result, okay, is called compensation theorem. This is another 2-port theorem, it's called. This is called compensation theorem. Any questions? Good? Yes.
Sir, instead of doing this, we can actually convert it to Thevenin equivalent and still do it. Because it's a purely resistive circuit, it won't, there's no power generation in it.
Okay.
So you can say the Thevenin voltage source will provide all the power.
Okay.
You can equate it to the power delivered by Vs.
Okay.
So you get the same expression.
How do you find out delta I1?
You can say the change in the power delivered by change in the Thevenin voltage and resistance won't change. Only R.
Yes. If you are, what you are saying is, if I understand you correctly, you are saying that I can find out the Thevenin equivalent here. Is that right? Okay. Then what do? I can find out IR plus delta IR. Correct. I can do all of that. But I think the point was, okay, the point of this problem was, I didn't want to do anything extra. I know the solution for case A. I don't want to do anything extra. If I want to calculate V Thevenin and R Thevenin, I have to go in and analyze the network. How do you find out V Thevenin and R Thevenin for this across 2 prime? Sorry?
You don't need to calculate it.
Then how will you do it?
In the last you get V Thevenin by R Thevenin plus R.
Okay.
They cancel out as IR.
Okay.
So you don't have to calculate the V Thevenin.
How do you calculate I1 then? You will get delta IR. How will you go back and calculate delta I1?
Well, V1 times delta, Vs times delta I1 will be the V Thevenin times delta IR.
Why is that? Because all the power is produced by this guy. Is that the result you are using? Yes, that is also an alternative way to look at that. Yes. That may also be fine. Okay. So now, before we move on to the next topic, let us quickly figure out, we have seen 4 types of 2-port parameters. Okay. Suppose we want to figure out which of these 2-port parameters are suitable for a particular case. If I just have a resistive network, you can actually calculate any of these 2-port parameters. They will all be equivalent and they will all be equally applicable, right? But there may be specific cases when one or more may not be applicable. You can tie this back to the original or the earlier case of Thevenin or Norton equivalent, right? If you try to find out the Thevenin equivalent of a current source, right, or the Norton equivalent of a voltage source, right, that won't be very easy or very useful, right? You will get these infinite parameters. If you take a current source, you got V Thevenin is infinity, R Thevenin is infinity, that is totally useless, right? So we want to find out something that will be useful, and you don't want parameters that have infinites in them. Okay? Suppose we take for a resistive network there is no problem. Suppose I take the case of an ideal voltage controlled voltage source. Okay? and let's say this was K times Vx. Okay, this is an ideal voltage controlled voltage source. I want to find out the two-port parameters, and I want to find out which two-port parameters will be most suitable. Okay, so how do you figure that out? Will what about will Y parameters be suitable? Will they be suitable here? What are Y parameters also known as? Short circuit parameters, right? So you apply a voltage on and try to find out the short circuit current. Can you apply a short circuit here while applying a voltage at the input? No, you can't, because you'll get an infinite current, right? That will obviously give you an infinity somewhere in the Y parameters. Okay, so you don't want to do this. So these will not be suitable for this. Okay, you can look at the other cases and tell me what about Z parameters. Will Z parameters be suitable? What do you need to do when you do Z parameters? You open circuit to find out the voltage and you apply a current. Can you apply a current at the input port? You can't, right? So Z parameters will also be not suitable. Okay, and what about H parameters? What about H and G parameters? What are H parameters? Can you go back and check your notes and tell me if H parameters will be suitable? Will they be suitable? No, they won't. Okay, you will find that H parameters are also not suitable, and only G parameters will be suitable for this particular case. Because if you take an ideal voltage controlled voltage source, it has an open circuit at the input and a voltage source at the output. So only one set of parameters will be suitable if you do not want any infinities. So what are the G parameters? So tell me what will be the G parameters of this ideal voltage controlled voltage source. Calculate it out. So you set I2 to 0, open circuit, the second port, apply a V1, okay, find out I1. What is that? 0. So G11 is 0. What is G12? This should be very straightforward. G12 is also 0. What about G21? G21 is K and G22 is 0. Okay. Your G parameters for this ideal voltage control voltage source will look like this. It will be 0, 0, K, 0. Okay, what is this two-port parameters? What does this matrix tell you? Well, if you had done the reciprocity requirement for G parameters for any network, okay, you will find that there is a certain relationship between G12 and G21. This does not satisfy that. Okay, so this is not a reciprocal network. Okay, you should figure out the conditions as a homework. This is non-reciprocal. More importantly, this is also unilateral. Okay, so this is not only non-reciprocal, this is also unilateral. Unilateral means the cause effect is in one direction only, not in the opposite direction. In fact, the opposite direction, the cause effect is non-existent. Any questions on this? If you look at the ideal voltage controlled current source, so let's say this was Vx and this was Gm times Vx. What kind of parameters do you think will be suitable here? What are you doing in the case of the you can go through all the parameters, but the basic idea is you need to figure out when the port can be shorted and when the port can be opened. Okay, very clearly the port 2 prime cannot be open circuited. Okay, when you apply a voltage at the first port, right? So you have to look at the parameters where port 2 prime have to be shorted. What are those two cases? Y and H. Okay. Will Y be, what about port 1? What do you do there? Port 1 can be short circuited also, right? And can you apply a voltage at port 2? Yes, you can. So the most appropriate parameters will be the Y parameters in this case. Okay. What do you think the Y parameters will be? The Y parameters will be 0, 0, Gm and 0. You can calculate that out for yourself. For a current controlled voltage source, so let us say some Rm times Ix. Okay, what kind of two-port parameters will be appropriate here? You cannot open circuit the, you cannot short circuit the second port. Okay, so, and you cannot apply a voltage at the first port. These are Z parameters. If you look at the Z parameters, you will get 0, 0, Rm and 0. If you look at the ideal current controlled current source, the H parameters will be the most suitable ones and you will get 0, 0, K0. Okay. And you can also extend this to the, once you know it for the ideal cases, okay. If I give you something like this, suppose I take this ideal case and I add a series resistance Rx what will happen to the H parameters? What will happen to the H parameters? What will happen to the H parameters? What will happen to H11? I'll get Rx here. What will happen to H12? It will stay the same. H21 will stay K and H22 will stay 0. Okay? If I had added an Ry here, what would have happened? If I add an Ry, what happens? 1 by Ry. I'll get a 1 by Ry here. Okay. So you can see that even for simple cases it's very straightforward to figure out what will happen. This is a non-ideal. This is an example of a non-ideal current control current source. Okay. In the case of an ideal current control current source, you had a short circuit and you had an ideal control source at the output. Okay. This is a non-ideal case. Why is it a non-ideal case?
Because the current is not exactly there.
Because the current coming out from 2 prime, when a second circuit is connected, let's say a simple resistor is connected across 2 prime, the current through that is not exactly equal to K times Ix. Okay, it is split between Ry and K times Ix, depending on the relative values of Ry and the R that you connect from outside. Okay. Say I take two cases and this was Vx, this was Vy. Okay, this current source is Gm times Vx, this current source is Gm times Vy. What are the H parameters of this? What are the H parameters of this particular network? What? Oh, sorry, you're right. You're right. You can't short circuit, you can't open circuit the either of the two ports, right? So it has to be the Y parameters. What are the Y parameters? What is Y11? Okay, go figure this out for yourself. I'll give you the answer. So you'll get 0, Gm, 0. Okay, these will be the parameters of this particular network. Okay, and is this reciprocal? Yes, it is. Y12 is equal to Y21, so this network is reciprocal. The point is, you can make reciprocal networks using control sources, but if a network has control sources, it is not necessarily reciprocal. Okay, that is all you can say about it. You can use control sources to make the network reciprocal also. Any questions on two ports?